Hello and welcome to this second class in the continuation course on measure theory and integration. So as I motivated last time, we need now to expand our definition of what we mean by measure to signed, and we're also going to use complex measures. This is not the definition, but to not keep you in the dark, let me just get to what this is about. So it couldn't be simpler. All right, so here you have it. Any signed measure can be written as the difference of two non-negative measures, so no, in the sense that we knew them from before, right? At least one of them should be finite. So for signed measures, we allow infinity or minus infinity, but we can't have both values at the same time. Basically, because plus infinity, minus infinity, it doesn't mean anything. Complex measure, same thing here, but now all four measures that we kind of need have to be finite, yeah, because well, we don't want infinity here at all. So the difference of two non-standard measures as we knew them before, plus I times the same thing, right? So this means if you insert a set A here, you do parenthesis A on all things, and instead of getting a non-negative number as we got before, in order to just get a complex number. So there's nothing strange to it. That's of course not how we define them. Of course, we could define them like this, but it's very ugly because then, well, I guess it's a matter of taste. Anyways, the way we do define them is we go back to the definition we had in the non-negative case. How should I call those? I'm going to say just measures, or sometimes non-negative measures, to be clarified when I talk about the, those how we knew them from before. But typically, if I say measure, it's a positive, sorry, non-negative measure. Signed measures, these guys. Complex measures are these guys. Okay, so how do we define these two? Well, I'll just go with the signed measures, and then you can make up yourselves what's the complex one. So definition: a function mu on some sigma algebra with values in the extended real line is a signed measure if mu of the empty set is equal to 0 and mu of an infinite union of disjoint sets AK is equal to the infinite sum of the UAKs. As before, we of course need to assume that these guys are disjoint. Okay, so if you have a complex measure, you just put here the complex number plane instead, and there you don't have, plus or minus infinity doesn't really fit in that picture, so that's why we don't want that. Right, so this is the definition. Now, how do we get, well, one way of getting naturally such measures is, remember, we were doing this, we defined new measures, new, if we had an old measure, mu, by writing like this. And this is a bit of a sloppy way of, I don't like this, there's no good notation here really, but what this really means is you define the new measure nu by doing integration of the characteristic function of A times F, the mu, or we can put A down here, right? So this we worked with before in 2.6 in the book. We had this, and then we required f to be non-negative function. But of course, that's a stupid restriction. Anytime you have an L1 function, f, this gives rise to something that has a meaning, yeah? So this number exists. If I put the void set here, I get 0, and by the Beppe-Levi or dominated convergence theorem, I think it is, it's a small exercise to check that we do have this. Should we do that? So this is a way of getting a measure, right?
Yeah, so if f is L1, use dominated convergence theory with g to be equal to modulus f, and fk, you do the sum. Okay, let's use big K here. So small k goes from 1 to big K, and then characteristic function of the AKs times f. So now this is a bunch of functions, fk, that converge pointwise to, characteristic function union. K goes from 1 to infinity, ak, f, that's the limit. And then you see, so if I do now mu of a finite union, right, so mu of the infinite union, I will just get this function here. Then I use the dominated convergence theorem to pull the sum and the limit outside. And then I'm here. Right. So yeah, so this gives us a signed measure, or if f is complex valued, a complex measure.
Lined up, so also really nice, beautiful results lined up today. So the problem is, well, this super simple definition, and then I told you, that it can be proven that then if you have the signed measure and you have a positive and a negative part, right? There's a difference of 2. But to get there is not easy.
So to illustrate here a bit, so if I now have we'll keep on this example. So the nu is equal to f times the mu, right? So here's my function f.
Then, if you think about it like this, there's like a set here and here, which you can call p, where the measure is somehow positive, yeah? And then there is another set, which is here and here, at least, where the function, where the measure is in a sense negative, yeah? Of course, there are other sets where the measure is, like take the set, okay, from here up to here, that'd be my A. And clearly mu of A is going to be positive, right? Because I have a small bit here, but the integral of this piece is not that big, if, at least with Lebesgue measure being our mu. So then this piece here gives a much bigger contribution. So this is a positive set in the sense that the measure is positive, but it's not a positive set in the sense that you have this piece here of, where the function is negative. So we kind of we don't want to talk about this as a positive set. So this guy P here, the white one, is in a sense much more positive. But how do we classify that, or how do we, characterize that? This is one question.
And another thing we can do with such a measure, okay, so this leads easily to positive and negative sets. So, well, okay, let's define that now. So, P for a measure nu is positive. Maybe it should be called non-negative, but no, we call it positive. If nu of A is bigger than or equal to 0 for all A which are subsets of P, right? And then N is negative if, and then it's the same thing, we just flip the inequality. All right, so that's one thing that we get easily for this particular type of measures.
Okay, so what else can we do for this particular case of measures nu arising like this? Of course, well, nu is here assumed to be a positive measure. Well, of course, this is the positive part, right, of the function. And here we have, this piece here and here, that's minus the negative part by definition. So we get, nu, okay, I use this notation again. The nu is equal to f plus the mu minus f minus the mu. So this naturally leads to a decomposition. I mean, this guy defines its own non-negative measure, right? Nu1. And here I have another non-negative measure, nu2, because f minus is a positive function, but non-negative. Right, so here we have a difference. So yeah, at the end of the day, nu is equal to nu1 minus nu2. As I said, we can always do this, but here it came very easily from just looking at this function. But in general, we don't have a function that does this. So how can we even find this guy and that guy to write that's a difference? Because clearly these are not unique, right? If I do here, let's say +1, yeah. Now I have a new measure, and then I do +1 on this guy also, and put a parenthesis here. I have another measure here, so now I get a new one and a new 2 again, whose difference is the original guy, right? Here I have to assume that mu is finite, otherwise I get some problems. But you get my point. You can always, so if you write f as f plus minus f minus, we can always add a bit to f plus and add the same to f minus. We get a different decomposition, yeah? So this is by no means unique. But of course, f plus and f minus are in some sense the smallest functions so that you have this difference, right? So we would like also in the measure setting to have like the smallest positive or non-negative measures, nu1 and nu2, such that the difference become nu. How on earth to figure, pull it out from this one equation that defines our what it means to be a signed measure? Well, we have two, but the first one is silly. Empty set as measure 0. Okay, so there are two key theorems. The first one is Hahn decomposition theory. So given signed measure mu, there exists. I'm going to stop talking about the complex ones for a while, because everything you can do for signed measures, you do mutatis mutandis for the complex ones. There exists positive sets P and negative sets, or a set of sets M, such that we have two important things. P union N is equal to X, the big space. Sorry, that was all there was to it. There exists this point. They're not really unique. We see that here, it's like here the function is 0, and here as well. I can either throw it in the positive set or the negative set, it really doesn't matter. But they are essentially unique. So if you have two different Hahn decompositions, I thought that was part of the statement, but it's probably some exercise or whatever. If you have two Hahn decompositions, then the positive sets differ only by a set of measure 0, and same with the negative ones. Okay, and the second key theorem here is the Jordan decomposition theory, which says the same. Given a signed measure mu, there exists,
non-negative measures mu1 and mu2 such that mu is equal to mu1 minus mu2.
And again, I thought the Jordan decomposition theorem had some sort of minimality statement in it, but that must be part of a a simple consequence. Okay, I leave it just like that. It's probably in the exercises that if you have with this particular choice, you're going to see how it comes out. Then if you take another difference yielding mu, then corresponding measure has to be bigger than the concrete one you get in the construction of the proof here, but it's not part of the statements. Okay, let's forget it. Anyways, so these are two beautiful theorems, and the proofs are super nice. So in the book, there are two first lemmas, which are somehow the signed measure counterpart of these two. No, what was it? Like 1, 2, 5 or something, you know, that we used a lot, right? If AK is an increasing sequence of sets, then the measure of the infinite union is the limit of the measure of the AKs. We use that extensively. So there's some similar stuff here in the beginning, but then I don't see it being used. And since at the end of the day, we're going to see that this, we're going to get this, right? We don't need these lemmas as far as I see it. What we do need, and where the beauty starts, is lemma 414. That one is great. So problem here is, so there are many subtleties here, but okay, so we want to find in the Hahn decomposition a negative set such that everything in the complement is like positive, right? If well, that's how we're going to do it. We find a negative set, and then we just define P as the complement. So we want to find like some maximal negative set. And you know, there are many sets negative, like this one. It's negative, but you can take out pieces of it which are positive, and then, you know, that's, well, right. So the measure is negative, but they're not negative, right? Because there's this piece here. So to get exactly this red guy and nothing of the white, it's a very delicate process. And even there are things in the proofs here which are hard to understand if you don't get into the mindset. Okay, so signed measures, you allow either plus infinity or minus infinity, but not both. But that doesn't per se, if you look at infimum of mu of A, of all A's, so maybe this is a finite number, but that can still be minus infinity. And you have the supremum, mu of A is equal to plus infinity. I mean, even if these are all finite numbers, there's nothing that says that this cannot happen. So that's another like complication that arises that we have to deal with. And they deal with it in a very elegant way. So the lemma 414, well, the lemma is not so interesting. It basically states that there are negative sets. You know, we can find, given a measure, a signed measure, we can find sets which are positive and negative in this definition, which are non-trivial. And even that turns out to be a, you know, a non-trivial statement. So proof is nice. Okay, so what we do, we start out. Okay, here's our big space X, and then let's take a subset A. I'm not writing all that, so we have a signed measure, yada yada. And now it's important here that it's strictly less than 0, and we also want it to be not equal to minus infinity, okay? So strictly less than is important. So there is some truly negative content here, right? So if you have this, you know, if we knew this decomposition into, you know, here is the negative part, and here is the positive part, and you would just say, okay, I take A intersect with the negative one, and that's my like maximum negative set. But I don't have this. This is, you know, I cannot use the Hahn decomposition theorem to prove the Hahn decomposition theorem. So there exists a subset of A which is somehow the maximum negative set, but we don't know that yet. We don't even know that there exists a negative subset, but we should do, because we have this like strictly less than 0. So what the lemma then says is that there exists a set N subset of A. Of course, in our sigma algebras, all these sets are in the whatever sigma algebra we work with. There exists n such that mu of n is less than or equal to mu of A. So, okay, maybe we don't get all this piece here that we are, the maximum piece, but we get some piece in here, which at least is big enough to counterweight the positive stuff here, right? So we will take out some piece here, which is big enough. Now there's okay, so this is the N from the Hahn decomposition. So maybe I call it NH and PH. Yeah, you don't get confused. All right, and now this is the N that the lemma gives me. Right, so we have this. And N is a negative set. And the way we're going to do it is actually, no, there's a lot of junk here. Let me paint this again. So here's the division line. So this is really an H. And what we're going to do is we're going to eat up this piece, the pH part, right? So we're going to start with the set here. Okay, they call it A1. And then we take another piece, A2 and so on. And they can stick in here into the negative part. That doesn't really matter. The important thing is we're going to design it in a way that we eat up all of the positive stuff, right? So how can we do that? Proof.
Too much A here. Okay, so E.
So look at the supremum of mu of E for all possible subsets of A and call that delta 1. As I said before, this might very well be infinity. And now we just want to, even if it's finite or infinite, you can never get a set that satisfies exactly your supremum, or most of it, we don't know that we can, right? Because if delta 1 is equal to 1, we're not certain that there are sets E such that mu of E is equal to 1. We just know that there are sets E such that mu of E gets arbitrarily close to 1. So we can always do pick A1. Now, okay. Now we're calling it A1, subset of A, such that mu of A1 is bigger than or equal to delta 1 divided by 2. We can do that. But now if delta 1 is infinity, that's no good. I mean, then we cannot do that, actually. So given that it's a finite number. So to deal with that, here I'm going to write minimum delta 1 divided by 2, comma 1. And then I know it's so this comma 1 is just there to make sure that this is a finite number. And then, of course, if delta 1 is infinity, then we can pick a set whose measure is bigger than 1. Okay. Now we're going to continue this inductively. So we set delta 2 to be equal to the supremum E subset of A, but now I subtract my A1. U of E, okay? And then we do pick A2 subset of A set minus A1. Such that again, mu of A2 is now bigger than or equal to minimum delta 2 divided by 2, comma 1. All right. And I keep on going like this. So delta 3 will be supremum E subset A set minus A1 union A2, right? And that's how you keep going. So here I would then pick A3 subset of A set minus A1 union A2. And note that this A1 and A2 are disjoint by construction. Okay, now, what is mu of the infinite union of the AKs? Well, okay, so this process here continues down, right? These are disjoint, so I can use my formula. And each one of them is bigger than or equal to delta k divided by 2. K goes from 1 to infinity. And now, okay, here I probably all right, so sorry, this is very subtle. This infinite union here, which in the book they call it A infinity, is a subset of this set A, which has a negative measure. So then the subset can't have infinite measure plus infinity. That doesn't work with this, right? Because then you would have mu of A infinity plus mu of A set minus A infinity. That's a finite number. Okay, so then both these numbers are finite too. So we have that infinity is, so this is a finite number, so this is a finite sum, which means that there can't be too many ones in it. So at some point the delta k's are going to be smaller than 1, and then we conclude that the infinite sum from 1 to infinity of delta k must also be a finite number. So in the book they call this here for B, I'm going to call it the same. And then what we're actually going to do is this set here, we're going to define that equal to B. Now, clearly this is also bigger than or equal to 0, right? So here I have a number which is bigger than or equal to 0, plus then of course a negative number because this is negative. So this must be more negative than that guy. Either a number is negative or it's not, but you get my point. More negative is a lower value on this one because here's a positive value. Or, no negative at least. So this one is less than or equal to that guy. So that's what we have here. Now the difficult part is showing that B here is a negative set.
So the point is, assume that what I'm going to call it E is a subset of B, and mu of E is less than 0. When?
Sorry, we want to prove that B is a negative set, so then it should be bigger than or equal to 0. But then, so this set E here, it will always sit somewhere here, right? So it's never part of the ones that we chose, yeah? So every time we do a supremum here over everything that is in the complement of what we have chosen already. So this supremum, you can always pick this guy E, and then that gives you, whatever positive value that has. And that contradicts the fact that this delta case goes to 0. Yeah? So that cannot exist. Boom, boom, and then we see that B is a negative set. Very smart argument, and now I'm tired. This was not my best explanation ever. I'm gonna call it a day, go home and continue tomorrow. Okay, so armed with lemma 414, we can now prove both the Hahn decomposition theorem and the Jordan decomposition theorem fairly easy. So here is X, here's my negative set, here's my positive set, and here's the division line, right? But I don't know this division line. A signed measure cannot take both positive infinity and minus infinity. You cannot have both values in the range. So let's say for concreteness a minus infinity is not in it. So assume that mu of E is not equal to minus infinity for any E in our sigma algebra A. So, well, I mean, if there are no sets whatsoever that takes a negative value, well, then the measure is positive. So then we're done, right? So we're going to do this set L to be equal to infimum A mu of or E maybe. Okay, so as I said, this number can still be minus infinity despite having assumed that. So here's a bit subtle. So what I'm going to do now is I'm going to use lemma 414 to pick negative sets. So let's pick an A1 here, which is negative. And then I pick another one, A2, and so on. I don't really have to bother about these ones being, growing or anything like that, that disjoint or whatever. So I just want them to, in the end, like the measure of it to attain the limit to get this L, right? So, and I want them to be negative. And here's where lemma 414 comes in, right? So if I pick an A1, which maybe has a piece over here, which is close to L, I can pick a negative subset of A1, which is even smaller, so then even closer to L, and that subset is negative, right? So with this little argument, we can right away from the outset assume that A1 and A2 and so on are negative ones. Okay, so well, it's short, this argument, but it is subtle. So what I'm going to do is I'm going to put N to be equal to the union of the AKs. First of all, N is negative. Because let's take some subset E of N, and then you just realize that E is equal to the infinite union
Yeah, no, that's not gonna work. So what we have to do is you consider AK minus the union of the previous ones, right? So set minus. So, for example, for A2, what I'm talking about here would be this piece, right? Now, the point here is that this is now a disjoint sequence with union becomes N, and then we intersect this with E, okay? So
now this is a disjoint sequence of sets whose union is E, and then I can use the infinite summation formula on this, right? So let's say, let's call these ones BK, then I have that mu of E is equal to infinite sum. This is the only thing basically we know about measures, right? So, and now each BK is a subset of my AK. So as such, because the AKs are negative, it must have measure less than or equal to 0. And then this infinite sum has measure less than or equal to 0. So E then has measure less than or equal to 0. So then n is negative. Okay. Now, in a similar way, of course, here I can write n like this, and then I don't have to worry about him. And then if we do this, if you break this sum up here in a part going up to k, and then plus another sum, k plus 1 to infinity mu of bk, then you see that here, this is just mu of my ak, right? And so this is a number close to L. Now, of course, these are negative or they're not positive. So here is a number less than or equal to 0. So this one is less than or equal to mu of AK for all k, right? But clearly, it's also bigger than or equal to L because it's a subset. So I mean, L was the infimum, U of E for any stuff. E, so N is one of those guys. So we have this. Okay, so this means that mu of N is equal to L. All right. So now the only remaining question is, okay, we got probably all of this, but did we miss anything? Is there any piece here that should also be part of N? So, in other words, is P the complement of N? Is that a positive set? Well, because, well, yeah. I mean, what we're going for here, we want X to be equal to N union P, right? So by that, we have to define P equal to X set minus M. And yeah, if we show that this is positive, then we are done. What the hell is going on with the camera that it's slowly moving? This is spooky. Fishy here. The ghost of the math department is present. Okay, and this is pretty easy. I mean, so if P is not positive, then you can find some subset. Let me call it B with negative measure. But then U of M can be is equal to mu of N plus mu of B, which is then strictly less than L, and that is a contradiction because L was the infimum. Aha! And I forgot to mention, remember we said in the beginning that we don't know that L is actually a finite number. And if it's not a finite number, this argument is wrong in various places. But here, up until this point, we don't use the finiteness, and we construct the set N such that mu of N is equal to L. Well, then L needs to be a finite number because we assumed this here. So many things to think about in this very short argument in the book. But yeah, it's the beauty of mathematics. Now, armed with this, so now I prove the Hahn decomposition theorem. Given any signed measure, you can divide your space into a positive and a negative set. Armed with that, we now get the Jordan decomposition theorem for free, which basically says that there is a, two non-negative measures such that the difference is a given measure. So Jordan against Hahn. Well, this is Hahn. And Jordan, well, it says that you can write mu as mu plus minus mu minus, well, these are measures in the classical sense. And the proof, well, it says mu plus to be equal to mu. Okay, let's define it like this. Mu of E is equal to mu of E intersect P. And mu minus is gonna be mu of, oh, that thing is now I have to do it again. mu of E equals to minus mu of E intersect N. And it's a extremely short argument to see that, well, I mean, it's almost follows immediately. So mu plus minus mu minus is going to be mu. And of course, this is non-negative because N is a negative set. So all these numbers come out less than or equal to 0, and then there's a minus sitting there. And what about some sort of minimality? Well, that's almost immediate now. So if you have some mu1 minus mu2 also equal to mu, we want to show that mu1 is bigger than or equal to mu plus. Well, let's just, okay, so mu1 of some set E is equal to mu1 E intersect P plus mu1 E intersect the negative set. And this is a positive number because mu is a measure in the traditional sense. So, or well, at least non-negative. So we get here mu1 of E intersect P. But if you reshuffle around, there's a mu1 is mu plus mu2, right? So here I have
mu of E intersect P plus mu2 of E intersect P. And again, this is a number bigger than or equal to 0. And this guy is by definition my mu plus E. So there you go.
Okay, so by now you probably feel pretty smoked, but unfortunately the material 4.1 is not over. It continues relentlessly with more difficult things which one needs to think to understand. But to give you guys a break, I decided like this, we cut it here, and because the next section about the Radon-Nikodym theorem is a bit shorter, so I'll squeeze in the end of 4.1 into the next lecture. So basically I lectured now until the end of the Jordan decomposition theory in 416. So where it starts talking about variation, that's what I will talk about next time. Thank you.
So it occurred to me here that I should probably add an instructive example. So if we let nu be a signed measure given by the Dirac measure minus the Lebesgue measure on R, where Dirac measure, I'm pretty sure we've come across it before. So it's a very silly measure. It gives 1 if 0 is a member of E and 0 elsewhere. So sometimes it's painted, you know, like a function which is just infinitely high peak here at 0, but that's not what it is. It's not a function at all. It is a distribution though, or a measure. But so distributions are more general than measures. Anyways, now I'm getting sidetracked. So for the Hahn decomposition theorem, to have a concrete example here, the positive set must clearly include 0. So the most natural Hahn decomposition is to take P to be equal to 0, and the negative set everything else. But to stress that this is in no mean unique, we can also say take P to be the rational numbers, because they contain 0 and the measure of the rest, non-zero rational numbers, under the Lebesgue measure. So some of the negative part is 0, right? So if we throw that in here, this is still a negative set. All subsets of this is 0 measure. All subsets of this is positive measure. Well, positive in the sense non-negative. Good, that was the example. And okay, of course, if for the Jordan decomposition theorem, there you have unique measure. So this is the positive part and that's the negative part. And yeah, well, unique in the sense of course we can add a bit to this measure and then just subtract the same thing here, but this is the one you get from the construction in the proof of the Jordan decomposition theorem.